Okay, so welcome back. So here's the theorem that allows us to be able to find the slope of a tangent line for parametric equations. Okay, so the theorem says consider the plane curve defined by the parametric equations x equals x of t and y equals y of t. Suppose that x prime of t and y prime of t exist, so that the derivatives with respect to t exist for both of them. And also assume that the derivative of x with respect to t is not equal to 0, as for obvious reasons as you'll see, right? Because we're going to be dividing. Then the derivative dy dx is given by this equality here. So dy dx is equal to dy dt divided by dx dt, which basically is the same as y prime of t over x prime of t. So we can get the slope of the tangent line by just taking the ratio of the derivatives of the corresponding parametric equations. Okay, now, so here's the proof. Okay, so let's start with our assumptions, right? So in this case, to prove this, it really just takes the chain rule. And so in particular, what we're going to do is we're going to assume, in particular, that we can eliminate the parameter. Okay, so in other words, we're going to say that y, which is equal to y of t, we're going to say that by substitution, and again, we've done examples of this, we can eliminate t. In other words, let's say this is going to be a function of x of t. Okay, so we're going to start with that. Okay, so we're going to start with this. Okay, so now naturally what we're going to do is we're going to, so here's the proof. So we're going to take the derivative of both sides. Okay, so how do we do that? Well, here we're just going to write this as y prime, right? So we're just going to take the derivative of both sides. Okay, so this is going to be y of t is equal to this, right? Okay, because if we're going to say that y, so let me start with this. So if we're eliminating, we're assuming that y, if we can eliminate t, is going to be f of x, right? But then f of x, we could just say that's the same thing as f of x of t, right? But y is really, again, we're saying y of t then, right? So we're saying y of t is equal to this capital F of x of t, okay? And again, this is just by using the substitution method that we've done in the last several examples of eliminating the parameters. So that's all we're basically doing here. So I'm writing y of t as this function of x, but realize that x is also a function of t, right? So now what I'm going to do is I'm just going to take the derivative of both sides. So if I take the derivative of both sides, I have y prime of t. And then what happens over here? Well, I've got an inside function, right? And an outside function. So the chain rule tells us that we take the derivative of the outside times the derivative of the inside. So this is going to give me capital F prime of x of t times the derivative of the inside, which is x prime of t. Now, I'm going to divide both sides by x prime of t. Now again, remember in the theorem, we're supposing that x prime of t is not equal to 0. So we can go ahead and divide both sides with no problem. Okay, so if I do that, I get y prime of t divided by x prime of t is equal to f prime of x of t. Okay, now, so far so good, right? So here I've got this, right? So I've got this piece, okay? Now, can I show that this is equal to this? Well, yes. Because what is f prime of x of t? Well, this is just equal to this, right? And this is y is equal to f of x. So again, what we're doing is we start with y is equal to just a function of x, right? Which is equal to, we can write it as this way, right? Because x is also a function of t, right? So it stands to reason that this right here is also the derivative of this. Well, what's the derivative of this? Well, the derivative of this is just equal to dy dx, right? And we're done. That's the end of the proof. See you next time.